Okay, so I got an announcement. Some of you responded to our call for interviews. So with the same project, now we're gonna we need as many people to take this inventory. It's an assessment that we're building to see how well students understand the concepts of Calc 1. So we're building this assessment. We need lots of trial runs, lots of people to take it. So I think I'm going to post an announcement on Blackboard. I can't do that because of the two-step authentication process. I don't have my phone with me. So I'm going to post an announcement on Blackboard, but the gist of it is it would be at 1 hour on either March 22nd or March 23rd. You'd be taking this pilot of this assessment, and it would be 1 hour, and you would be paid $30 cash when you're finished. Okay? So I will post that announcement on Blackboard right after class, and we need as many people as possible to do that. Again, March 22nd or 23rd, 1 hour of your time. Do your best on the assessment, and then you can walk away with $30. So I'd hope to look at, hopefully I can get to web work by the end of class. I wanted to look at the most commonly missed or troublesome items on today's web work, but again, I can't do that. So we'll just go on to the new stuff, or keep going. So we've got our feet wet with sequences here. What is a sequence? What is a sequence? A list. It's a list of numbers. Got to know that before we know anything else. A sequence is a list, okay? And we saw a couple of key things from last time, that we can write a formula, right? A formula based on the nth term of the sequence. So some formula in terms of n that will give us the nth term of the sequence, and then we can analyze these sequences to say whether they're convergent or not, convergent or divergent. If it's convergent, that means all the terms are getting really, really close. In fact, as close as you want to specify to a particular real value. Meaning specify a distance from that real value, as small as you want, and there's going to be some point in that sequence where you're going to get that close and always be closer after that. Okay? If anything else is true with the sequence, it's divergent. It's divergent. Okay? So this is about we saw this is about limits. Okay? So let's look at some common forms of sequences. And here's one over end of the p. And remember we said that sequences are like, we can think of them as a function, right? So if I was to write the associated function to this, say, call it g of x, what would the rule for the function be that would be associated with this sequence? 1 over x to the n. Is that right? 1 over x to the n. What would it be? 1 over x to the p, right? 1 over x to the p would be the function that would be like the cousin to this sequence. At integer values of x, you get the exact. So when x is a whole number, you get the exact same terms as the sequence, right? So when x is 1, 2, 3, 4, 5, then you get exactly the sequence. But then this function then is also continuous for all values of x. That's how it's different. But we saw that the limit as x goes to infinity of 1 over x to the p will equal the limit as n goes to infinity of 1 over n to the p, or f of x, or g of x, right? The limit as x goes to infinity of g of x will be the same as the limit as n goes to infinity of 1 over n to the p. Because whatever the function does at its whole values, that's what that sequence is going to do, because that's what the sequence is. It's taking all the whole values of x, and those terms will be exactly the same as the sequence. So we actually talked about this when we talked about improper integrals. That limit right there, when does that equal 0? Equals 0 when what? Remember? Okay, when p is greater than 1. Is that right? So what about 1 over x to the 1/2? So certainly when p is greater than 1, this is going to go to 0, right? 1 over x to the first, 1 over x squared, 1 over x to the 10th, 1 over x to the 1.5. But what about 1 over square root of x? That's x to the 1/2. Can you get bigger? That's going to be divergent. 1 over square root of x. Not sure? What does square root of x do as x? Just think of what it was square root of x do as x gets really, really big. No, square root of x. Square root of x. It gets really, really big, right? It gets as big as you want to get, right? So, all you have to do is take x squared and you got the same thing as 1 over x, right? So what about this limit? 0, right? This is going to be 0. So for what values of p does this limit equal 0? Remember that? P is, I think we called it r before. We called it r before, but now we're going to call it p. We're going to call it p now. We're going to call this a p sequence. P sequence, 1 over n to the p. Okay, so let's actually, maybe I should have had you done this first. See this? Think what? When you see that, what do you think? Write it out. What does that mean? I should have. That's the first question I should have asked. Can you write out, mathematically describe what that is saying? 1 over n to the p. Did you get it? How about right here? Looks like you stopped writing. Yeah, did you get it? No, you, and with the glasses. No, right here in the gray sweatshirt, the young lady. Did you get it? Not sure. How about right behind her in the white shirt? Yeah. Okay, so you're analyzing just that, but I'm saying this whole expression, what does this whole thing signify? Trevor? N to the negative p. Okay, so you're just rewriting it mathematically. Okay, I'm glad I asked this question. I know Gabriel knows. Katja? 1 over 1 to the p? 1 over 2 to the p? 1 over 3 to the p? What is a sequence? A list of numbers. A list of numbers. Okay? Make sure when you see a sequence, you have this image of it. It's a list of numbers, and that formula is telling us how to build that list, right? How to build that list. Okay, so we've got the corresponding function, and then so we know the corresponding function, its limit is 0, or it converges to 0 when that p-value is greater than 0. And so therefore, same thing holds for the sequence. Okay? So if the smooth continuous function goes to 0, then the discrete points will also go to 0. Okay? So this is one way to say that. That thing will go to 0 as n goes to infinity if p is greater than 0. So this is called, we're going to call this a p sequence. It's going to show up a lot. It's a common form. We'll see it a lot. Okay, another one. This is called a geometric sequence. Geometric sequence. So let's start by writing out what this means. Is the same as what? See that? Think what? Go, write it down. See that? Think what? Okay, this side. How about in the pink shirt? Right there. She wants r squared, r cubed, etc. Did she get it? That's it. So let's think about this. So what is it happening here? We've got this number r, and this is called a geometric sequence. We're going to have a geometric sequence. And we'll call this a p sequence. Okay, so a geometric sequence. What's happening? Every time we go to, so how do we get to get the next term? What do? We multiply by r again. So that's basically what's happening. Every time you've got a term, to get the next term, you multiply the last term by r. Starting with r, then r squared, r cubed, r fourth. All right, so for what values of r will this converge? For what values of r will this converge? Think about how when you keep multiplying by the same number over and over and over again, what about that number r would make that converge? Can you imagine that? Robert?
Well, if your lines converge, would it be 1?
Okay, so what if r was 1? Would that converge? What would it converge to? 1, right? So yeah, so that's like a special case of this. When r is 1, it converges to 1 because you just keep ending up with 1, 1, 1, 1, 1, 1, 1. Okay? So that's a special case of this. What about other values of r? Yes, sir?
It's got to be greater than -1 and less than 1.
Okay, so he's saying numbers between -1 and 1. So like fraction numbers, like 7/8, 1/2, -0.1. What happens when you keep multiplying? They're going to get smaller, and then you're going to say it's 7/8. You're always going to be taking 7/8 of the previous value, 7/8 times 7/8 times 7/8 to get the next one. So what will that converge to? 0, right? What about if r is greater than 1? Boom, it's going to blow up. Right? What about like a negative? Say -3/4. Divergent or convergent? -3/4. So what's going to happen now? It's going to alternate, first of all, right? It's going to be negative, positive, negative, positive. But we saw last time that can be convergent. Remember that? So just say if r is -3/4, will that converge to 0? Yeah, because all the positive ones will get super small to 0, and all the negative ones will also get super small to 0. So it's going to kind of do this and converge on 0. All right, so outside of 1 and -1, it blows up. Inside of 1 and -1, it's going to converge to 0, and if it is 1, then it's a special case. Okay, so our Rn will approach 0 as n goes to infinity if r is between -1 and 1. And then it'll approach 1, this is kind of a trivial special case, if r equals 1. So again, we'll refer to this first one as the p sequence. My son is potty training right now. We know all about the p sequence. Geometric. All right. So this is how we'll talk about those. P sequence is 1 over n to the p. Geometric sequence is r to the n. So where p is a constant or r is a constant. Okay, so now we're going to your homework for Friday will be practicing analyzing sequences for convergence or divergence. Okay, so here's some. They're all different. So there's this. It's not. There's. You have to kind of have some savvy and some experience with it. So here's some suggestions. Okay. Consider the associated function, right? If the associated function, whatever its limit is the same as what the limit of the sequence will be. Okay? Just list out the first several terms. Get values and just kind of eyeball the pattern. All right? So use algebra. Use some algebra on what you're given to manipulate things. Pre-calc knowledge. And then there's just some common sense involved in these things. Okay? And then the common forms. So you're on the lookout for the common forms. So these ones that we've talked about. Okay, so let's do some practice now. All right, so the first thing we want to do is practice writing out the first three terms of the sequence. In other words, you see this, you think what, right? You see this, you think what? And then we're going to analyze each one as convergent or divergent, and we want to state your reasons. So that's not just a one-word state. You're going to write out at least a phrase, maybe a sentence that explains how you have deduced that it's convergent or divergent. And if convergent, determining what the limiting value would be. Determine what the limiting value would be. So maybe let's do, before we do those, let me just do one here. Like this. Let me do one. I'm going to do this one example, because this is something that will come up a lot. Okay, so for this one, so we could ask the question, is it geometric? Is it a geometric sequence? No, geometric sequence is a constant to the n. A constant r to the n. Nothing like a geometric sequence. Is it a p sequence? 1 over n to the p. No, okay? It's not that. So one thing we could try here is think about the associated function, right? Think about the associated function, which would be, I'll just call it f. F of x equals 3x to the fourth minus x squared. And then notice I've got, what's the degree down here? What's my leading term? 4. So I'm going to change the order here, get them in order. Negative 2x to the fourth plus x plus 5. Did I change something? Did I write it? Did I recopy it well? Okay. So whatever the limit of this is as x goes to infinity will be the same as what the sequence does as n goes to infinity. Okay? So now this goes back to pre-calc knowledge. This is a rational function, and you talked about horizontal asymptotes. The horizontal asymptote is asking the question, what happens to this? What happens to values of y as x gets very large positive and very large negative? So this becomes something you have done in pre-calculus before. So what is the limit as x goes to infinity of f of x? So do you remember doing those problems? Do you remember doing those problems? You take a look at, you compare the degree of the numerator and the denominator. How do they compare here? They're the same, right? So as x gets really, really big, what's going to happen? So say you have 1 million, right? So like a million squared versus a million to the fourth. What's a million squared going to be like compared to a million to the fourth? Yeah, so this is going to kind of disappear as x gets really, really big. Even if that was x cubed, x to the fourth would be a million times greater than x cubed. And then now go to a trillion. X cubed is a trillion times greater than, x to the fourth is a trillion times greater than x cubed because you multiply by a trillion one more time. So everything that's not the leading term will basically fade away to 0. Same thing down here. And so then as x gets large, we essentially have 3x to the fourth over negative 2x to the fourth. And so what is that? Negative 3 halves. So remember doing these problems? So if the limit of that function is negative 3 halves x goes to infinity, then the limit of that sequence as n goes to infinity is also negative 3 halves. Okay, so that's one way to do a problem like this. You set up the corresponding rational function, and then you apply this horizontal asymptote idea, right? The limit as x goes to infinity of that thing, and that's about comparing. What if the degree in the denominator was greater? The degree in the denominator is greater, then what's the limit? Remember, the limit is 0. What if the degree in the numerator is greater? That's just going to blow up, right? So if the degree in your numerator is greater than the denominator, then that is going to be infinity or negative infinity. The degree in the denominator is greater, then it's 0. The limit will be 0. And if they're the same, then you can do the ratio of the leading coefficients. Like in this example. Now another technique for these is we can do some algebra on this. We've got n to the fourth is our greatest term, so we could divide all terms by n to the fourth. So some of you may appreciate this technique. And now, what does each one of these little things look like? 5 over n to the fourth. What is that? Okay, but do you recognize what that is? Yeah, it is 0. But so now each one of these is its own little problem. As looking as n goes to infinity, that's a p sequence right there, right? And is p greater than 1? Greater than 0, right? All p has to be is greater than 0. So that goes to 0. This is really 1 over n squared, right? Another p sequence with p greater than 0. This one is 1 over n cubed. P sequence with p equals 3. So what's left is, what? 3 over, and so this would go away. N to the fourth, this is just 3, and this is just minus 2. So as n gets very, very large, all these as p sequences are 0, and then what we have left on the numerator is positive 3, and the denominator is negative 2. So we get the same result. So those are both valid ways to approach that. Divide by the highest power of n, all the terms, and then use the common p sequence individually on those terms, and then or convert to the rational function and apply the rules of comparing the degrees of the numerator and denominator. Questions on this example? So what is this? What did we just find out? We just found out that as you take more and more terms, these terms are going to get closer and closer and closer to negative 3 halves. In fact, as close as you want, as long as n is big enough. As close as you want to negative 3 halves, as long as n is big enough. Yes, ma'am?
For the second way that
Yeah.
you showed, if the degrees of the numerator and denominator were different,
It'll still work out.
so just the greatest.
Yes, still, yeah. Divide by the greatest degree. That's right. And it'll still work out. Other questions? Okay, so now you guys practice. So for Friday, you're going to have more web work and a written assignment, just practicing lots of sequences, analyzing lots of sequences. So first, write out the first 3 terms of each sequence, or if it's really ugly, and so for time's sake, just 2 or something like that. But just, again, imagining what you're looking at. You're looking at a list of numbers. What is the list, right? What is the list? And then analyze for convergence or divergence. Okay, ready to talk about them? Here we go. A. Problem A. How about right here in the white tank top? Sir, yes, you're up on A. What do you think? Convergent or divergent? Because? All right, so yeah, so obviously the numbers are getting big and they're alternating and getting bigger. So we could say divergent. So do we recognize what we have? Recognize what that is? Geometric, right? So this is divergent geometric sequence. Because -4 is what? Less than -1. It's outside of that range for convergence to 0, right? For geometric sequence, the range for convergence is between -1 and 1, and it converges to 0. Because you keep multiplying a fraction times itself. But if you have a number that's bigger than 1 or less than -1, it's just going to get bigger and bigger like we're seeing. Okay, B. Let's see. B. How about in the pink shirt and the black hat right here? Did you get B? What did you think about for that one?
I forgot to do that.
What's that?
I forgot to do that.
You forgot to do that one. Well, that's convenient. I'll come back to you, okay? How about in the gray shirt? The red hat.
Which one?
B.
I said convergence of 1/3 because they're at the same degree. Sine of 1/3.
Okay, so we're going to look at just this part. Let's look at this first. What does that converge to? 1/3, right? The degrees are the same. So like x squared over 3x squared minus 7, that function approaches 1/3 as x gets really big. So then if that thing approaches 1/3, then what will this do? Convergent to sine of 1/3. Okay, and so then your reason here would be the math, right? So you'd show the math on this that converges to 1/3. I don't have room to do it, okay? But do the math like I did in the example before these on that, and then you can say that therefore this sequence converges to sine of 1/3. Okay, how about C? Right here in the Zoo York shirt. C, part C. What'd you think about that one? And why? Right, it's a convergent P sequence with P equal to? What is P equal to in this case? 1/2, right? Which is greater than 0. As long as the power of n in the denominator is greater than 0, that's a convergent P sequence. So it's a convergent P sequence, P equals 1/2, greater than 0. Next one, D. How about down here, right here? Great. Yep.
Is it divergent?
Divergent, because?
It's just going to be like 1 and -1.
Right, so this is divergent because it never approaches any particular value. So you could write that out. It never approaches any particular real value. It just keeps hopping, 1, 0, -1, 0. So don't average the values. Don't say it converges to 0 because that's the average of all the values, right? If it converges to 0, that means you say, you take the number 1/1000th. Sometime in the sequence, then all the terms have to be within 1/1000th of 0. That never happens, right? That never happens. And then take 1/1,000,000. At some point in your sequence, all the terms after that point have to be within 1/1,000,000th of 0. That's the idea of convergence. This does not do that. Okay, E. How about in the blue t-shirt here? Yep. Because?
Because the numerator has a higher value.
Okay, so comparing the degree of the numerator and the denominator, what's under the radical is going to diverge. Therefore, the square root of a divergent sequence is still going to be divergent, right? So yes, you're going to analyze this underneath first. So divergent because the rational function diverges. Because the degree of the numerator is greater than the degree of the denominator. And then because that rational function diverges, certainly the square root of those values is going to diverge. Okay, F. How about right here? Black tank.
I said that converges to 0.
Okay.
It's a geometric sequence.
Converges to 0 because it's geometric. Agree with that? So what? Yeah. So that's the same as what? 1 over. Yes. Yeah. So the geometric is when the n is the exponent. Yeah. So maybe you just said the wrong thing. Yeah. Yeah. So it converges to 0 because this is a p sequence with p greater than 0. All right. How about G? How about G? Who got G? Let's see. How about you, sir, in the white t-shirt? Yep. Converges to 5 or 3. And how do you know that? Okay, but careful. So now, but see, that would be true if the n's were the base like this, like a polynomial. But here are the n's of the exponent, so it's a different. When the n's of the exponent, what are we doing with them? That's not like a rational function anymore. Okay, how come? Okay, right. So this is the same as we could also write this as what? Pi over 3 all to the n. And then what do we have? What is pi over 3 all to the n? What kind of sequence is that? Geometric. And how do we know if a geometric sequence converges or not? We look at that value of r, right? So that's our value of r. R is greater than 1. Pi over 3 is greater than 1. So you have a number greater than 1. You keep multiplying by itself over and over again to get the next one. What's going to happen? What's that? Yeah, it's going to get big, right? So if that value is, just think about it. Any value that's greater than 1, if you keep multiplying by it, it's just going to keep getting larger and larger and larger. And so this is slightly greater than 1. But we're going to be multiplying forever, right? And so it's going to get big. So this is going to diverges because this is a divergent geometric sequence. Happy Pi Day, by the way. 1 day late. Happy belated Pi Day. All right, what about the last one? Go for it.
Converges to 0.
Okay. Careful. So let's make sense of this here. What's 3 to the n plus 1? What does that mean? 3 to the n plus 1. How many 3's is that? How many 3's multiplied together is that? 1 more than n multiplied together. So we could rewrite this like this. You see that? This is going to be really important when we get into series. You're going to see all this kind of thing all the time. 3n to n plus 1 means we're multiplying a bunch of 3's together. N plus 1 of them. So you could, it's the same thing as multiplying n 3's together and then multiplying by 1 more 3. That should make sense. Does that make sense? You've got to see exponents. Again, you see that? What do you think? Oh, it's a mess of 3's multiplied together. How many? Well, n of them and then 1 more. So I can rewrite it this way. And then what happens? We get what? 1/3 of the same one we had before. Convergent or divergent? Divergent. Divergent. Taking 1/3 of numbers that get really, really big, it's just going to still get really, really big, just a little bit slower. Okay? 1/3 as fast. Okay? But this is still going to get really, really big. Doesn't matter. Multiply by 1/1,000,000th. It's still going to get really, really big. We never run out of ends, right? We keep going and going and going. So this, for the exact same reason as the one above, is divergent because it's geometric with r greater than 1.